Okay, testing. I'm back. Well, to start a second video now, third video. So, as I was talking about earlier, we're going to be going through the game map this time. And the game map contains a 2D array of tiles, a list of scenery objects. It implements the persistable, which is a custom file. It's an interface that I'll go over later for cleaner code. It basically makes it easier for saving and loading. And we will also get the tile class. We'll actually go through the tile class first because it's a big part of the game map. So this is the tile class. It has a name, an image, a sprite, a tile index, and a walkable boolean. The walkable tells whether a tile is walkable or not. This tells the game map, because all this information lives in the game map, and only the game map has access to the tile's position on rendering. And so the game map will collect all the tiles in a list and have their boolean flags there so that the game state can access it to determine whether or not something will happen when something collides with the collision box of the unwalkable tile. There's also, there's a sprite library to get the appropriate sprite. There's a get image from the sprite library, which is used to load the tile by taking the tile's name, and then it'll get the image based off the tile's name. It's instantiated and the sprite is generated. So to generate the sprite, it'll take the sub image from the tile sheet based on the tile sheet size, and uses the game sprite static variable so that it can cut it to the proper tile, which is currently 64 by 64. And then it uses the get image from the sprite library to generate a sprite, and it returns that sprite from the tile sheet based on the width and height. So each tile is indexed based on the tile sheet from top left to the bottom right. Has so I'll show you the tile sheet. You saw it in the editor when I showed you earlier, but let me just open up. For example, this custom one, that it's a tile. You see 1, 2, 3, 4, 5 by 4, so it's 20. But it doesn't have to be a square or rectangular like that. I've also don't know if I still have it. Let's see. No, not this one. I think I overwrote the file. Yeah. So I had initially a large tile sheet that had maybe like 5 or 6 different tile sheets all at once, and it all works fine. It'll display them all in the tile menu without any issues. But I wanted to play around with the auto tiling, which is why I did the smaller tile sheets, since the logic was handwritten and manually mapped to determine the possible combinations for the tile map. And I'll go over, as I said before, the auto tiling at the end of all the videos, because it's something that I want to delve deeper into, and it's something that is a lot more complicated but very useful. It's just a very time-intensive technique to use. But if I ever want to implement a auto-generated type of terrain game, I would definitely need some sort of auto tiling in order to determine what tile should go where, and it's a very cool thing to implement. Okay, so after the generate the sprite, it has reload graphics, which will just generate the sprite again, and we'll get into why that's necessary, because it's part of the serialization. So the persistable implementation, which I'll go over right now, is just an interface that will hold the static variables for the delimiters that we use for parsing. So like the colon is used for regular delimiter. The section delimiter would be the 3 hashtags or pound keys. I actually don't know what they're called. Um, the list delimiter would be a comma and a space, and then the column delimiter would be a line separator, and then anything that implements persistable must implement serialize and apply serialized data, which is the way that the objects are turned into text or reconstructed from text. And over here, I'll go through in detail how that works. So in this example, we have the tile. The tile will first, the serialize will first instantiate a string builder, which will then get the class name, and that'll be the first item inserted. Then the delimiter is placed. Then the second item, which is the tile name, will be appended, followed by another delimiter, followed by the next field, which is tile index, followed by delimiter, followed by text field, walkable, and then it returns the string builder to string, which the game map will then have all this information for when it saves the map. And to apply the serialized data, it just reverses the entire process, so it will split based off the delimiter, and then that first token, not token 0 but token 1, will be the tile name, and then it'll do the tile index, which is based off of the parsing the integer on token 2. And if there are more than 3, this is just a check, because initially when first creating the tool, there was no walkable boolean, so the older maps it would cause an error if there was no check to see if there was a larger array size with an extra field, because it's a new field, so that's how you go about loading the older maps. And then there's a method to allow the tile to set itself to be walkable or not. Okay, I already went over the serialization. Oh, and the copy of is also important. So we have a copy of function here, which will return a copy of the tile with the same information. This allows for when the map is being loaded to flag something as walkable or not, regardless of the default setting for that tile, because each tile has like a default value, whether it's false or true. Like for example, the water has a false value since it's not walkable, but you can flip the flag and then make it walkable in the editor itself. So you're not limited to making a hole be unwalkable. Let's say if you wanted to create a secret passage, like the old games where you would have something that's normally not walkable, but then it's a secret passage, so you could just walk through the wall or something like that. So that's pretty cool. Now we're gonna go back to the game map, and all the tiles are stored in a 2D array, which is instantiated. It's based on the size, and the size, it's gonna take basically the sprite size and turn it into like a grid size, so that we have an XY grid position. So it'll be in the 2D array, and the game map will be like an X by Y grid. It also has it'll fill the array row by row. So this is an enhanced for loop that'll take tiles and then fill one row with the tiles from that row, move to the next row, fill the tiles from that row using the tiles constructor, using the library. And then we have getters and setters for the width, the tiles, the height, and then we have a function here called getRandomPosition, which will just return a walkable position on the map, so we can use this for spawning enemies randomly on the map and not have them spawn on something that they can't walk out of, which currently is not as big an issue because only the unwalkable tiles are preventing them currently. But as I said earlier, I forgot to include the scenery collision handler into the update, so that they weren't being updated. I had done that issue earlier with the player character as well, and I fixed that, and I forgot to do it for the NPCs. Okay, so then this is just a boolean which tells whether or not there is an unwalkable scenery on that tile. So when it saves, it'll check to see if the collision box of the scenery collides with a grid with the grid on that position, and then it'll know that this tile has unwalkable scenery. So it'll determine that that particular grid space on the map has this tree which is unwalkable, and it'll return a list of any scenery. Oh, I'm sorry, it'll return a, not a list, but a boolean. Then there's the get viewable starting position, which will show the first grid all the way, and there's one for the ending grid position, which will show all the way up to the last grid. And this is just used for calculations to determine what grid you're on, and it's also used for calculations. There's a grid within bounds, so if the grid is within bounds, that means that the grid is in the viewable space, and or it's also used for calculations to determine whether or not a particular position is something that the game should make any calculations based on. So like it doesn't want to calculate anything outside of the game map grid. There's a set tile function, a method. I keep saying function because it's C++, but a set tile method, which allows you to set the tile at a particular grid position. And then there's the reload graphics, and for the same reason, when we are loading and serializing things, we want the reload I didn't explain it, but the reason we have reload graphics is because when you serialize the data, you don't want the image to be stored. We just want the string to be stored, and then the images will be loaded upon the game's instantiation. So when the game starts, it'll load the images then based off of the string, which is why we have a tile name, and scenery has a name too, so that we can match the name to the file that corresponds to that resource or sprite. This is a method that returns a list of collision boxes for the unwalkable tiles so that the game state can do things with it. And then the collision box get grid collision would just allow the game to check if anything is colliding with a certain grid position. So like the other method was telling us that, oh, there's a scenery that's on this grid that's unwalkable, and the only reason it knows that is because it creates a collision box on the grid that checks for any scenery. There's a getter for the tile to return the tile array, and then a list that just returns all the scenery available. There's a set scenery list, which will set the list when loading the map, and then the serialized data, and this one's a little bit more complicated because it has to take into account the tiles and the scenery. So it'll first construct itself with like the tile length, both the X and Y of the tile, and then it'll take a section and then put in all the tiles, put in a column delimiter, put in all the tiles again, and then arrange it that way. I'll show you how that looks like. It's readable, but not super readable. So as you can see, everything is separated. This is similar to how you did it in class with the tile builder, but your tile builder used single characters, and I don't anticipate ever spending much time manually parsing these texts myself, and I leave it to the editor and the game and the code to do the work for me. But if I ever needed to come in here and take a look at something, or if I wanted to make it more readable, I would have to adjust the formatting of the delimiters. And these are the tiles. These are whether or not it's walkable or not. And because this is the boss room, there's no scenery. But if we go to the dungeon entrance, there's another section here, and it shows you all the positions and all the information needed to reconstruct those pine trees. And it's a very long list, which even if it was more readable, it would be very unfun to parse with your human eyes. And so applying the serialized data just reverses the entire process. It splits it based off of the first limiter, and then it splits it the sections, which are the comma, the line separators. So then it'll have the tile section and the scenery section, and then reconstruct the entire map, load everything in, and reload the graphics, with the serialized information, and now you have a saved game map and a way to load it. Okay, and that's the end of the game class. We're gonna go to the game state now. And actually, in my notes I take care of this later on, but I'll go over it now. So in the state, we have a couple of methods that I haven't gone over yet. Aside from the mouse input, which is just checking to see where the mouse is clicked, and this was only used for some debugging, which is telling you that the mouse was clicked at this position. There's a sort objects by position. This is used for sorting the Y position. So when we render, if your player is above the Y position, which is, a lower Y position than another object, the other object will be drawn in front. So it gives you that illusion that the object's in front of you. And it just uses the comparator to compare the simple rendering, the render order and the Y position. So it also has like the render order as another variable to check against first, and then it'll organize based on the Y afterwards. There's a list of game objects, the getters and setters for the camera, tile, state, set time. Oh, time. I forgot to go over time. So I will go over that right now. There's the set health, which is just a functionality that hasn't been implemented yet. An abstract get player, which needs to be implemented by others, but it was just used for some testing and passing around some stats. The list of colliding game objects, which returns a list of all items that are colliding with another game object, and then it collects it into a list so that we can use that for handling collisions. A getter for the UI containers that house all the UI interface. This is a special stream. It just returns a stream list of an object that extends game objects. So it could be scenery, it could be NPC, it could be player, or it could be game object, or it could be moving entity, any sort of game object. It'll return it in a list so that we can parse through that list and do things to one type of game object versus doing something to every game object. The sprite library getter, the spawn, which allows an object to be spawned onto the map during the game, and the despawn, which similarly removes an object from the game. Getter for the health, the getter for the input, the set next state, which will put the next state based on the state that's inputted into the argument. So if I wanted to go into the menu state, it would put in the menu state as the next state, and then the next state would go through for the update. It's also setters and getters for game settings, audio player, the cleanup for the audio player, which just stops all the music, mouse handler, which will, it's just has to be implemented even though it's not doing anything specifically. That's the getter. And then the load and save game map. So load game map will take the file path, it'll check if it's an instance of game state, because for my transitioning logic, I don't want the player to be cleared from the game objects list. And I could similarly use the stream and just choose to clear objects of NPC type, but I also want to clear the scenery because I don't want scenery from the other map to be on the new map. And then I use a remove if, which is a list feature to remove objects that meet a certain predicate, which in this case is not game object of player. Then the game app will load the new sprite library, the file path, and it'll add all the scenery into it. And the map IO, it's been unimplemented, but initially it had been the one that handled the opening of the buffer for the writer and the reader, but it's now been changed to the persistable IO, which has a more robust saving and more generic saving and loading system, so it doesn't only open one type of file. And I save the text files as a WRL, which is a custom file. I just shortened it for world. So the persistable IO, we have the save, which is just opening the file path. It checks to see if the file path is null. If it's null, then it's going to throw an illegal argument, but ideally we would want to check to see if the directory exists in that file path, and if it doesn't, we create the directory, and using the file.mk make dir, which basically means make directory folder, and then save to that. But that is something that would be implemented in the future. As for loading, it'll load an object. It doesn't know what object yet, so it has to be an object that extends persistable, which is like something like game app. Or if I wanted to, for example, save like a high score, I could give it the persistable class, and it would be able to save that to a text file, and then it'll load that based on the class that you type in. It'll open up the file path, check to see if it's null, and then return an argument if it is. If not, then it'll just open up the buffered reader and load the file and go line by line reading everything and apply the serialized data just to reconstruct whatever object is being made or class from the text file. Okay, now we'll go to the game state, because save map, get window size the same, and this is just some other mock-up code that I was using to demo for my group mates what we could do for a group project. Okay, and I don't know if you know how to nest the packages properly. I would love to hear that, because I have packages within packages, and for some reason they just all want to show, and I couldn't find the setting in Eclipse to fix that. So I just want to make this easier to see. Okay, so now we go to the game state. In the game state, it has a list of victory and losing conditions which aren't currently implemented. The tutorial that I was following along with had it set so that it would count the amount of healthy people and sick people and determine whether you win or lose based on a metric. So like, for example, if there were 25% of the characters on the screen were sick, it would be considered a loss, and it would pop up a menu button. But that's not how I would have it in my game. Would be a completely different type of game. It would be based on health, and so getting health to 0 would be the loss condition, while the win condition would be like beating a boss or collecting an item from a dungeon or something like that, because that's the type of game I would want to make. It has a string array containing the path to all the game maps. This is a 2D array that I implemented to imitate sort of a grid-based system. It's initialized manually, so I would in the future change this to have its own class for the initialization, but currently based on the map structure that I have, you can see like the start was 1-0, because if I don't know if you recall, but I had 5 total vertical screens and 1 screen to the left, so everything starts on the 1 position since everything is on the right side, and then the screen on the left is at the 0 position. So I'm constructing a map in a 2D array. It's hopefully it's easy for you to visualize, but that was my intention with the way I did it, and this was just to print out because I was having a lot of issues with the transitioning, which I was talking about with the colliding, the collision boxes colliding with the invisible collision box multiple times in one update, and that just wouldn't allow it to transition properly. And also my mistake with the Y being lower at the top of the screen and higher at the bottom of the screen. And okay, back to the top so that we can continue going down through the list. The game state also has a player object so that the player is persistent, so that when we clear, we make sure that the player's information gets transferred, it goes to the next screen. Then the game state calls super on, let me just explain this. I just had the music change happen here, but ideally I would have different events or event objects that would change music based on where I am. Currently this is just a manual hard-coded check so that once I'm in position 4, which is the highest Y position of the grid, the things are getting weird .wav will be playing instead of Molly's World.wav. And first it clears and closes the other thread and then goes into the game state also after being instantiated, it has to initialize the room values. The game map is a new string based on how big I want the game maps to be. So like if I want to make a 10 by 10 game dungeon or something, I would do that, and then I can manually map it out. Or if I do a randomly generated, that would be more ideal. But that's something for the future. And the maps are initialized through that method that I showed you earlier. Then the map is loaded, and right now it's currently set to map start.wrl, but I could easily put in the get resources of game maps at current room X, current room Y, and that'll return the same string. This was just done because I was doing a lot of debugging for that feature that I had put in. Then the game settings are initialized, and they're set to false for the whether it should render the grid, because that's, we don't want to render the grid when we're in the game state. That's only for the editor. So like if you leave the editor with the grid state still on, it'll automatically be set to false when you start playing, and the playing value is set to true. The characters are initialized and the UI windows are initialized, and I'll go over the UI later on, but that's going to be a brief section. So after that, we have the game state, and it calls super. This is all the logic for initializing characters. It just chooses the position for the player, and it initializes the NPC. So there's only 5 NPCs, and then this is just some logic that I was messing around with earlier. And then we add the objects, the players to the object list, and the camera focuses on the player, and then play is also set to player. And then this was part of the other like tutorial win condition that I was playing around with just to see how it would work, but it's not used in my game. Then we initialize the UI window, which as you can see, it's very similar to how CSS works. It's basically borrowing from that concept of margin, padding, vertical containers, flexbox, and all that. So it's like sort of a Java implementation of web development techniques and web building. The initialization of the NPCs just takes a loop, goes through the loop, and creates new characters, new NPCs with their controllers, their image, takes in an argument for how many NPCs we want, and it'll set their positions at a random location based off that game map random function that I went over earlier, and adds them to the game objects list. And then the game is update. It just calls update on super.update, which is brings you back up to the state. And that's similar sort of to like a state machine almost. It's not exact, it's actually not like a state machine, but it's similar through how things are done in, for example, React in web development, where the state gets passed along and it goes up and down a chain. The lose condition was what I was talking about earlier, based on, I would change it to the health being 0, and the win condition would be based on winning a certain thing. Enter menu brings you to a new state by removing all the current containers and then putting in the new container based off of whatever state we're currently entering in. This is just for making NPCs sick, which I will talk about later. The getter for the player, some more stats about number of sick, number of isolated, number of healthy NPCs, as well as the number of NPCs in general. And then getters and setters for the room, the initialization of the game maps, the setters for the room too, and the return of the game map string that shows all the strings and is used to load the maps. Okay, over that. We talked about the UI and the CSS similarities, position, flexibility. Okay. We talked about entering the menu. I already talked about those state classes. Okay, so we will look at the UI now, a brief overview of how it works. So we'll open up a bunch of menus. We're going to start with the vertical containers. vertical container will nest UI elements beneath each one another. So it'll first start one at the top and then one beneath it, and it takes into account the combined child height and width. And basically, it's just like CSS. It'll take padding, margins, and separate each element, and then create a container. And then you can nest things. Since it's a container, it can have children, and children. These are all extending the UI container, which has all these features that you would find in a web development thing. So like you can center the children, you can change the background color, you can change the alignment to a start, end. Or I currently only have 9 positions, which is start, center, and end. And it's a relative positioning too, so it can be either with the game screen or within the element itself. It can organize based on the alignment. It has a list that holds all the UI components. All containers are UI components, but not all UI components are containers, because a UI container can hold other components, but can also hold other containers, since it's also a component. There's an absolute position and a relative position. The absolute position calculates with respect to the screen position, while the relative position calculates with regards to its parent container, so that everything is nested and properly sized. The calculate content size takes into account all the content size, and it adjusts the container size based off of that. And the padding, you can set it to have a fixed size or not. You can calculate the position. This takes into account the absolute, the alignments. So the alignments are just basically like this one. The center will calculate it based off the middle, the exact middle, while the front and end are taking it. It's a arbitrary value that I just chose for it to be like not too close to the left side, but more towards like 2 tiles or so. But it's also based on relative position, so it's calculated differently when it's nested within another container. Like each container can have a sprite, and each container can update itself and generate its own sprite. You can add UI components, set background colors, set alignments, set a fixed size, center the children, remove components, clear components, check to see if a component is inside the container. And next we'll go over the UI text. And you saw me go in here earlier to adjust the font, but this will be a UI component that sits inside a container and just renders a string to that container. So this is how the play and all those menus were created, because the text would be written here and then it would draw itself. It also takes into account the font metrics. I, based off of the person that was teaching me, we don't know a better way of getting the font metrics without creating a small canvas at first just to get the font metrics. But the reason we do this is because depending on your font, if it's not a fixed width font, the size of the string is going to be varying, and to keep everything consistent, we want to have that font metric in order to determine the width of the string and calculate the UI component size correctly. Another thing that we want to talk about is the tab containers. So the tab containers, it's just like how we have tabs up here, and it works the exact same way as you saw in the video. I was switching between the tile sheets. Each one was labeled. Tab container has a nested class of tab because it is something that only lives and should only live in a tab container. Tabs and tabs go together. It extends the UI clickable, which is the way that the mouse consumers that I talked about earlier. It's how it keeps focus. So if it has focus, that means the mouse is contained within the absolute position of the container, and then it'll set that element as the active consumer. So whatever is supposed to happen when the mouse clicks onto that container is going to happen while not clicking through the other side and placing the tile accidentally, or clicking another setting. So if I had a whole bunch of menus stacked on top of each other, the one on top of everything would be the one that would get the focus. Similar to how it works on the windows. Like when you have a window in the front and you click on it, it's not going to click through behind it. So that's the whole purpose of this clickable UI component. Okay. Oh, it keeps going way ahead of myself. We're going to talk about UI image. This basically allows for icons and images. It's just a quick way of displaying an image. It'll display a component that's just an image, whatever the image is, whatever you want it to be, whether it's an icon, a sprite, or something else, just like how I had the pine tree displayed in the scenery tool. That's done through this UI image here. There's also the divider. There's only one currently, which is the horizontal divider, and that just makes it easier to it splits like down the middle of a container so that it can separate objects, and in design principle, like things like gestalt, things that are grouped together or associated with one another. So if you remove that divider and things are just squished up once again, you're going to be thinking that, oh, the auto tiling and the tile walkability are related, but they're not related. They're their own tools and they're their own different things. So we want to divide them, and this is just simply a design UI thing. It doesn't really contribute otherwise. It's just for design principles, and it's easy to implement the same thing but for a vertical divider. So if I wanted to do the same thing in a vertical container and divide things, I would create a vertical divider and have a horizontal bar that separates the two elements or UI components from one another, or whether it's a tab container from another tab container. Like, it's just for organizational purposes and design. Everything has access to padding. So we have the padding and margin, which uses the spacing class, which holds the top, left, right, and bottom. And that's just an int that's subtracted or added onto the size of the container to create that padding and spacing. Once we're done with that, we're going to go back to the state. Oh, actually, no, I already talked about the loading map. We did the map IO, we did the persistable, the save, I did that. I got the declare constructor, I went over that. Sorry. We talked about the mouse handler in the save. Okay, now we're gonna go into the update methods of the game itself. So and the update, it updates everything. So the way it works is that, not the game state. I need to organize the code a little better. Which goes to, okay. So this is the main update thing. The time. How could I forget about time? Let me go over that really quick. So the time is just a way to make the seconds that have elapsed into a human readable form. So instead of seeing 200 seconds, it'll use the modulus operator to get something divisible by 60, and then it'll format it using a string builder to create the time format that we're all used to, which is the one with the colon and the zeros, and then that's the whole purpose of this. It's just basically for a timer, and it also keeps track of how many updates since the start. Okay, so back to the update function. The update, first, it updates the audio player, it updates the time, and then it sorts everything by the position. Then it updates the game objects, and then it takes a copy of the UI containers to iterate through and update each individual container, once again to not deal with the concurrency modification error that will happen if we try to change the state of a UI container while iterating through a list. The camera is updated, the mouse handler is updated, and then it also checks to see if there's a next state. Otherwise, it continues being in the game state, which is where it currently was. Okay, so we're gonna go into the update method. We're gonna go into game objects next, because the way the update method works is that it uses once again, to avoid the concurrency modification error, it'll go through a for loop, iterate through the entire list of game objects, and this also enables it to be sorted at all the times, and it'll call each game object to update itself. So it'll go through a loop based on the size, and they'll each update themselves. And so for game objects, this is like where the fun begins. Game objects are what our entities are, and our scenery, everything that is on screen that moves or that isn't a tile is a game object. Well, and that isn't UI. So it's like things for animations, things like bubbles or the claw effect that I was showing you in the game. Also, there's rect in the entity, but it honestly doesn't belong there, and I would move this to the core package. I just have been focusing on implementing features and haven't done that much refactoring in this last week. But in the future, I would move that over there. Which reminds me, I should go through the core first before going to the game objects. So let's put that on the back burner and go through all of these here. Some of them will be familiar because some of them are the same code that you provided us in class, and some of it is used, some of it is not used. But we're going to start with condition. And condition is just a simple interface. It just returns a Boolean whether the condition is met or not. So if the condition is met, then something happens. Or you can have a list of conditions, and once all those conditions are met, then something else can happen. So you could use it maybe as a flag in the game to determine, oh, you've gotten this event item, this quest item, now the game will move on to the next state, or a new event will open up. So that's what it's for. Position is just, it stores the X and the Y. Proximity range is used for determining, I'll talk about that later, but it also implements persistables, so because everything has a position on the screen, so it has to be able to save that position, and we need a persistable if we want to save it. It holds the double X, double Y, and that's what consists of the position, but it also has a constructor to do an int instantiation of the position, because a lot of pixels, you can't really subdivide a pixel, so we need that. And we have getters and setters as well as double getters and setters. We have a means to return a copy of a position so that we don't mess with the original position. We have a means to set the position, set the Y position, the X position. We have a means to apply a movement to the position, which I'll go over the vectors, but the movement will apply, it'll grab the vector and then it'll apply that movement vector to the X and Y position, and that's how we get some movement in the game. The is in range is that proximity range. So for one of the AI states, which is wander, it has a target location that it wants to reach, but sometimes it might not be reachable. For example, something might be in the way, or it might overshoot it because it's going too fast. So once it gets near that position, it'll stop. It'll just, its goal has been accomplished. It doesn't reach that exact position, but it can be fine-tuned to make it get closer and closer to the position. Apply X and apply Y just applies a movement in the X or Y axis, while adding position allows two positions to be added without having to separately add to each x and y position. Same thing for subtract. Distance 2 is it basically just returns the square root of the x and y position, which is the distance, and this is really important for a lot of calculations, especially for calculations involving going to a certain point and trying, or if I wanted to implement an A-star algorithm, I would have to use this as some sort of cost identifier in the serialization. Okay, so we're going to do the vector now. And vectors, this is a lot of this we went over in class. It's a lot of the same functionality, except it's been put into its own class instead of having it all in like all over the place. There's a way to get the normal, so you can normalize you'll take the length, which is basically the same thing as the distance from before. It'll return the square root, and then we have the normal, which we can use to do vector calculations. So if we want to multiply by a certain speed, we have a multiply function that'll multiply both the x and y by that speed. We have a function to return a copy of the 2D vector, and also a direction between positions. So this is how it determines what direction it's going in, by taking the x and y and getting the difference between them, and then that'll be normalized, give you a direction which returns a new vector direction, and that's also used to determine the physical direction that the character is facing. There's a dot product, which if something's perpendicular, it'll return 0, just like basic vector calculations. A return getter and setter for the double y and x, or just the getter, and the vector addition, so we can add two vectors together without actually having to separately add to the x and y. And we went over the size class earlier in the video, but it's basically the same thing, just getters, setters, toString for the debug, setting the size, copy, serialize, and yeah. Now, movement. So this is how things move. It takes in a vector and a velocity, and then it uses that to calculate the movement. So based on how much speed it's going, it'll use the normalized vector, the unit vector, to change the position by x and y based off of the speed and the vector direction. So you have standard things like returning the vector, setting the vector, getting the vector, the velocity of the vector, setting the velocity, checking to see if it's moving. So if the length of the vector is greater than 0, we know it's moving. We can multiply vectors by a multiplier, so that's just a scalar value. It'll lengthen the vector to make it faster. There's a stop, which will just stop both the x and y vectors should it choose, and it's a ternary you can stop one position. If I want to just stop the x, I can stop just the x. If I want to stop just the y, just based off of the arguments inputted into this method. Then the vector 2D get direction, which is what I was talking about earlier, returns the vector with the direction, and you can add vectors to the movement, which I guess is redundant because the vector also has that. The lookup I didn't use, but I got it anyway just in case, because I was thinking about implementing projectiles as circles and having them shot out, and using, like, I was thinking about homing projectiles, so I like the idea of the chase and shooting a circular projectile at the character, or maybe shooting them at enemies. The line function I didn't use, but I used the Java line to draw the grid lines, which is the same thing. It takes a starting x, an ending x, a starting y, or an ending y, and then it draws a line from the point A to point B. So yeah, I didn't use this one. I used the Java one. The direction is just an enum that checks from movement the direction, and then it'll grab the vector, and it'll check the x and y values and do a cardinal system that's based on 8 points of direction. So it's just a if return, and otherwise just returns south facing, and then it'll also provide the animation row based off of the direction for the animation, which I forgot to go over, so I'll go over that really quick. And so the animation manager is very similar to what you created. It has, instead of being labeled delay, it's just updates per frame, which is the delay for the animation. It has a constructor. It'll take in a sprite sheet, the updates per frame, the index that you want the frame to start on, the current frame time, direction index, so that it can choose the right row for the right animation, whether or not it's looping, and the animation name. And then it'll play animation stand if not moving. And it'll get the sprite by getting a sub image based off the frame index. So that's, it takes the direction index to get the right row, and then the frame index is just the current frame of the animation. When it updates the direction, the frame time gets pushed up, and the direction index is also gonna return a new row. So if you're moving, that'll change the animation while it's moving. And animation size is just based off of the sheet's width. So like, as long as the width is, that row is how many images would be there. So if I have a 10 frame animation, that'll be a width of 640 pixels, and it'll take each one at the 64 because that's the game sprite size setting. It also checks to see if it's looping, which is what you did in class, but this is just using a ternary operator. It checks if it's looping, it'll go back to 0. If not, it'll stop the animation at the last frame, which is what this does right here. And then it has the ability to play the animation, which just plays the animation from the starting index, and then that's what we have over here. Okay, and now we're gonna so the movement vector, I forgot to mention, is then put into the the controller receives input, whether it's from AI or a physical user input device, and then that sends the boolean that's used to check what direction the character is moving to do the movement calculations. Let me show you. So over here, it'll check to see whether you're requesting left, right, up, or down, and then it'll change the movement vector based off of these. Or for the NPC, it'll just check requesting up, right, left, or down, but that's based off of AI, so it's not gonna be directly like controlled by the player, and it has a way to just stop everything automatically. And this is just to determine that proximity range that I was talking about earlier. So like, if it's within the proximity range, then it'll stop or it'll go towards it. So now I do have the circle class but I've only used it just to draw a selection circle, which I'll talk about later. I did want to create projectiles, but I didn't have enough time, and yeah, but that's why it's in here. And I would have removed, ideally I would clean up everything when I use it. So hopefully I'll get to implement that at some point, and that'll be pretty cool. Okay, collision box, the last one. So collision box is just, it contains the rect from the rect class in class, and it just checks for overlaps and returns collision box based off of the position and width and height of the game object. So it contains a rectangle, and it does some quick checks using the overlap function method. Now we're back to the game object, and I'll use this as another pause in our video.